Wait. Good afternoon, everyone, and welcome to this short webinar on the basics of COMSOL Multiphysics. My name is Sander. I work as an application engineer for the Benelux office, and today I will be going through the use of COMSOL as a tool for numerical simulation. COMSOL Multiphysics is a package that allows you to model your either scientific or numerical model using one of the available interfaces, and our product is so-called modular based. We have various physics branches like fluid flow, heat transfer, electromagnetics, structural mechanics, chemistry, and acoustics. And on top of that, you can also perform optimization, both for objective optimization and topology, which is then of course usually related to structural mechanics. It's also possible to insert your own equations or make additions to the weak forms that describe all these physics, because remember, we're using finite elements to model these things. And it's also possible to use our interfacing to link our product with MATLAB or Excel or one of the many CAD programs that are available. That all results in a model or a COMSOL file, and that's what we call a model. And then there's also a possibility to make an extension to that and make an application or a graphical user interface that can be used to help people understand what you're doing, or to distribute those using two separate products that I will talk about in a second to people who don't have COMSOL available. And finally, there's also a possibility to add custom reports, basically templates that are filled in by the program. All right. Now, if we take a look at the product suite of COMSOL, as I already told you, it is modular based, and we already went over these various physics branches. And if we take a look more detailed, we see that those branches consist of these modules that I talked about. Now, how does that work? First of all, when you start using our product, you always use this. That is the platform product, and that contains the essentials or the basic necessities to build your model. So to build the geometry, the mesh, solve it, and evaluate the physics. You will always need that. And then based on the physical need, you start adding the modules we have over here in the 4 physical branches that we have. To go over all of those is beyond the scope of this, but if you have any detailed question, there is a chat window, which I probably should have mentioned at the start, but you can put in your question there regarding this, and then at the end, I will take some time to go over that. On top of the physical modules, there is also the multi-purpose module, and I already mentioned the optimization part, but there's also a material library, which is very convenient because it allows you to very quickly assign material properties, and also, for example, dependent material properties, such as temperature, dependent conductivity, resistivity, to the materials of your need. Particle tracing, which has a application, of course, in electromagnetics, such as charge particle tracing, particles in fluid flow. And finally, here we see all the interfacings. I already mentioned MATLAB and Excel. And here we see a list of the various CAD programs that we can interface. So if you're familiar with one of those, know that you can combine that functionality with the COMSOL interface. All right. Before I continue, I'm just going to quickly check if the chat window is working on my screen over here, which you can't see because of the interface, but let's have a look. And it seems to be working. Yeah, that should all be okay. Then let's go back to the main screen. Now, there's one thing I still have to mention, and maybe I have to go back one slide, and that is the possibility to make applications or graphical user interfaces. And basically, those are graphical representations of the whole physical model. And the idea is that you build something that contains the whole model itself, but doesn't show all the things in the background, like the mesh, the physics, the numerical derivations. It just shows you the input, possible input, and the output in a way that it is understandable for most people. And once that has been built, you can distribute that to people who don't have COMSOL, either using COMSOL compiler or server. And that is what this slide is talking about. Starting with COMSOL compiler, that constructs a complete standalone application. So basically a separate program that anyone can run on their computer. And COMSOL server allows you to host your applications on a server or website, as you would like to say it that way. And both have their distinct advantages and properties. And the main distinction is that with COMSOL compiler, you can make a whole list of programs that people can use. But of course, if you need to update that, you need to release version 2, version 3. Like with COMSOL, we're now at version 5.5 and 5.6 is quickly coming up. COMSOL server doesn't give the user a direct model, but basically allows access to your model on that server that you're hosting. That means you have a bit more managing and organization tools to your disposal. All right. If you look at COMSOL server, then basically it can be hosted from any website, but we also have clients, so products that allow it to run on Windows and Android. And the nice advantage is then it works even a bit more smooth. So that's quite nice. All right. And that actually already brings me to the demo, which is the bus bar. And this is sort of the ultimate benchmark model in our package. And basically what a bus bar is, it's just a bent copper plate connecting by some titanium bolts to an external circuit. That means we have a potential difference and such a current is going to flow. And we're studying the DC case over here. Now, because of that, we get resistance in the material, like any material has, and that causes resistive heating. So we are interested in the current path, but also in the heating profile of this bus bar. So we both have electric currents, as the interface is called, and heat transfer in solids. And that's what we're going to study. So there's one thing more. So here we see actually the material properties. So we see the copper bus bar and the titanium bolts with an applied voltage or potential difference of 20 millivolts and a ground, meaning that the potential is 0 at these two lower bolts. All surfaces are cooled by natural convection, except the contact surfaces, because we assume that is connected to some external circuit. And natural convection basically means that the surrounding air is going to cool this bus bar, you could say, moderately. The equation that we're solving, in addition to the electric currents and the heat transfer, are of course the source of heat, which is calculated using this relation. And that's then being used as a heat source in the heat transfer. And that should be balanced by the conduction we see over here that happens inside the bus bar. All right. Let's go to the COMSOL interface. And this is the main COMSOL environment that we use to build our models and evaluate our results and such. What we see over here is that we have the layout where everything happens. So we have some model ribbons on top. That's very similar to any type of CAD program. That is one option. There's also a model tree with the components. And talking about that, we see that we have a component with a certain geometry, which represents the bus bar, as you can see in the right hand of the screen. We have the two physics interfaces, namely electric currents and heat transfer, and we have a so-called multi-purpose branch with something called electromagnetic heating, which is going to tie them together. And I'm just going through this to show you how that works. Very important to know, and that's sort of part of our modeling strategy, which I would like to stress, is that we have geometric parameters, which are used in the sequence you see over here. So like the length, bolt radius, thickness, width. And we have something called a heat transfer coefficient, which is going to be used in the heat transfer, and the applied voltage. So I'm going to use that, of course, in the electric currents. Before we do that, however, let's work from top to bottom. So our geometry is finished. That's already done beforehand. But now we see that we need to assign materials indicated by the warning here. So I'm going to use our library for that, which I mentioned earlier. And I'm going to use copper. There we go. And I'm going to assign titanium. And titanium I have to assign to the bolts, and I have to be careful because the bolts, oh, misclick, are of course are in this model consisting of two separate domains. There we go. Now, you see, as soon as I click these domains, COMSOL automatically recognizes what type of material properties are needed to close the physical equations. And looking at the electrical equation, that's of course the conductivity and the permittivity, the relative form, of course. And for the heat transfer, we have the heat capacity, Cp, the density, rho, and thermal conductivity. And the same applies to copper, but then of course the values are different of these things. That makes the materials different in behavior. So that closes the material properties. Now let's have a look at the electric currents. And this is the equation we're solving for. And that's basically the current density is equal to the charge, or the divergence of the current is equal to the charge. And that is related via the electric field to the potential. Now that's the equation, and we have a so-called default or natural boundary condition, and that states that the current normal to all external surfaces is 0. And I'm content with most of that, but of course not on the contact surfaces of the bolt, because there I want something different. So I'm going to use boundary conditions to state a different condition there. Starting with the electric potential on this surface, and remember that was my parameter which I can access using this called V total, which was 20 millivolts. And I'm going to use a ground, and a ground is basically stating that the potential is 0 at the lower parts here and here. And that actually already closes the electric currents. Now the second part, and that's the heat transfer, of course. Looking at the equation, this is the form that we're solving for. And actually it's even more simple because solids don't flow, so we can neglect this convection term. And that means that we have this term, and that's the diffusive flux, or the Fourier flux, and that should equal any heat sources. Now the thing is, the heat source is of course originating from the resistive heating here, and that's actually already taken care here, which I will show you in just a second. What we need to do here is again check our boundary conditions, which state that this thing is so-called firmly insulated, and that seems to be the case because all normal heat flux is 0. And that actually is not what I want, because I want to go to a stationary case where there is some cooling occurring on the surface. So I'm going to call for a heat flux boundary condition, and more specifically a convective or a Newton's law cooling boundary condition, where I'm assuming that this whole complex behavior of fluid flow and cooling is all captured in this nice coefficient. And then the temperature of the surface is evaluated to some reference temperature, which is the temperature of the air. And if there's a difference, there should be cooling occurring over here. And that is active on all surfaces, with the exception, of course, of the contact surfaces of the free bolts. There we go. Let's realign. And now that we have done that, let's have a look at the heating source. So we have the electromagnetic heating, and that's the multiphysics feature, which solves this equation. So here we see our heat transfer equation. Oh, and we see how the electric source is evaluated, which is the product of the current density and the electric field. And that yields a so-called source called QE, Q electric, and that's implemented directly into the heat transfer, both for the solid part and the boundaries. And that basically is all I need to do. So let's have a look at our mesh. And COMSOL has what is called a physics controlled or default mesh, which I can make somewhat finer. I can make somewhat coarser, but for now I will just stick with the normal size. And that actually means I can go into the study and solve this for the stationary form. And I press compute. And this should be relatively quick. Yeah, there we go. And the nice thing is that if you have a study, it always generates some default plots, like this electric potential plot, which you can see goes from 20 millivolts onto 0, as we should expect. And these two temperature plots, one for the surface and one that is drawing isothermal contours. Especially if you look at the latter one, we can see that the main sources of heat seems to be originating around the bolts, and that from a current conservation standpoint makes sense, because the current conservation is of course indicating that the current should be conserved, and that means it's mostly constrained in these bolts, and especially of course this single bolt, because then the surface area is the lowest, hence the current density will be the highest. And that's exactly what we see over here, since the current density at that point seems to be concentrated the most, and we have the most increase in temperature over there. Now we can also highlight that a bit more in this original temperature plot by modifying the color range a little bit, and then by moving down the maximum. And if I do that, basically what I'm doing in that case is I'm highlighting the areas more where this cooling is occurring. Of course, you have to be wary that the results are now not representing the full thing, but for a visual standpoint, that is quite nice. Okay, let's return to the slide for a second. And that's basically also the conclusion of this webinar, where you can get some more resources. First and foremost, of course, there's our website where you can request a trial and download our product. If you do that, we have a lot of models like this and applications available, which are completely built out and with instructions, which makes it very easy to learn that, in addition to the manuals we have available. We also have a lot of videos in our learning center, and that's always a good place to start. But also if you're a more intermediate user, it's still very good to have a look at that, because it also contains more detailed topics, which I would say are not the thing you would do in the first 2 weeks when you work with this program. And the same thing goes for the blog post. We have some introduction stuff, but most of these blog posts actually are already dealing with much more dedicated topics. And from time to time, even I still go there to look at some info, and they can be a great start to help you modeling your tools and your setup. All right, that actually brings me to the end of this webinar. So I will see if there are any questions. And I see that there are some, so I will answer those, and after that I will close this. So let's see if I can expand this window a little bit. And I can, that is nice. Okay, one question from Janielle. It is if it is possible to simulate electrolysis in COMSOL. Yes, and that's done if we go back to the slides here. I might have to skip back a little bit, but you might want to take a look at the chemistry and the batteries and fuel cells module, or the electrochemistry. I think the electrochemistry is the one you should be looking for. Another question, which modules are used for this example? That I can actually check pretty quickly by looking at my model and going to file and check licensed and used products. And this model is quite straightforward. So that one just uses the base product, and that's all there is. So if you just have our base product, that should be sufficient to build this. One more regarding the nuclear magnetic resonance magnetometer. I think that is something you would have to request more in the support deal, or with someone from your own office. It is possible to simulate magnetism with our AC/DC interface, but this question seems a bit dedicated. So I would refer you to the to your local office, and based on your last name, I presume that it is Germany UL. So I would go there. But I think if you take a look at the AC/DC module, you will very quickly find if that will work. One question from Carlos: if you use 5.5, do you get 5.6? If you buy a license, then updating is included in that, if it is of course within the moment that you buy the license. But considering that 5.6 is about to release very soon, Yeah, that should be the case. A flat membrane separation. That seems detailed, and also with contact mechanics. I would recommend to have a look at the solid mechanics in that case. Manikandan, I hope I pronounced that correctly. Best way to start learning COMSOL from scratch. Do this busbar model. We have that, of course, in our library, but also the full documentation. And after that, use the Learning Center to get more through that on a regular basis. And practice makes key. So I would say Asham, again, hoping pronouncing that correctly, to do that. And once you get the hang of this, then it works. And what we usually also recommend is that people follow one of the trainings, because that usually is one of the better kickstarts for this. Okay, I think we had all the questions. So thank you all for attending. I hope you enjoy your day, and maybe until next time. Bye.